In this video we're going to look at how to model real-life phenomena like population sizes or the amount of radioactive materials in terms of exponential and logarithmic functions. Now, there are some things written at the top of this page which you don't necessarily have to memorize, but just be aware of. If you have exponential growth, then you have an equation that was going to be whatever it is your population, let's say, is going to be equal to some constant times e to the power of some constant times the amount of time that you've got. Now, that can equally well be written as the same constant times b to the power of t, where b is some other number. Right? So you can write things in terms of b, or you can write things in terms of e. Generally, if you know that, for example, things are doubling, every year or something like that, then you would have a b be equal to 2 there, and you'd have a 2 to the power of t. So sometimes it's useful to write it in this form, and sometimes it's useful to write it in this form. But we shouldn't worry too much about that for the moment. We'll get a better understanding of this later. If we have exponential decrease, then again you could write it the same way as you have up here. It's just that here the b will be a number between 0 and 1. Or you can equally well write it as a constant times e to the power of negative kt. That has the same effect. You have exponential decay there. Now in example 1, we're actually given the equation straight off. We're told that the mass of the population of some bacteria is given by this formula here, that the population is equal to P naught, that's just one kind of constant there, times 1.02 to the power of t. And it gives you some information. It says initially the population has a mass of 12.8 grams. In other words, when t is equal to 0, the population has a mass of 12.8 grams. Now that's actually going to give us some information about this equation. What it's going to help us with is to find out what P naught is equal to. Because we know that after 0 hours, it's going to be P naught times 1.02 to the power of 0. Anything to the power of 0 is going to be equal to 1. So we know then that 1.02 to the power of 0 is 1. 1 times P naught is P naught. And we know then that the initial population is going to be equal to 12.8. So that P naught is going to be equal to 12.8. So we now have a new equation. We know that the population is equal to not just P naught, but 12.8 times 1.02 to the power of t. In other words, we've figured out that P naught is equal to 12.8. This P naught basically is just the initial population. It's the population when t is equal to 0. So we have a better equation now. We can now use that equation to figure out what t is equal to when this whole thing here is going to be equal to 20. So that helps us to set up an equation next. Right, our equation is going to be this one here. Now, from what we've done in the previous section, you probably can guess how to solve this. Right, you can solve it by, first of all, dividing by 12.8, both sides. Then you can take the log of both sides, like this. You can then move that t to the front so that we then have this equation, and then divide both sides by log of 1.02 to get 22.5 hours. Now, we also have this type of problem, right? This time it's an exponential decay type of problem. And you can tell that it's a decay problem because we've got a a minus kt up here. Now in this example, it says that it's known that for bone, 99% of the carbon-14 is present after 83 years. So if you wanted to guess from that, if a bone was discovered with just 90% of the carbon-14 left after a while, you could guess that the bone's going to be a little bit older than 83 years. So we need to solve some of these, we need to find out what k is equal to in this example. Okay, so to do that, what we do is, first of all, plug in 83 in as t, so we have 100 e to the power of negative k times 83, and that should be equal to that 99%. So we have an equation here. This equation is just an exponential equation. The next obvious thing to do would be to divide both sides by 100. And if we do that, what we'll get is this equation. We can write that then in logarithmic form, like this. And then finally just divide both sides by negative 83, and we'll get k roughly equal to 0.000121. So our equation, right, if we go back to this equation up here, we've now found out what k is equal to, so we can replace k with that negative 0.000121. So we have an equation now that works for us. So the next thing to do is to try and figure out how old the bone is going to be, if the percentage goes down to 90%. So we're going to have this whole thing here not equal to 99%, but it's going to be equal to 90% instead. Okay, so we'll do that. We need to solve this equation. Right? 100 e to the power of negative 0.000121t equals 90. We can divide again both sides by 100. We'll get this. We can then rewrite that in logarithmic form. We'll get this. We can then divide both sides by the number before t. We'll get this. We'll get 871 years. And that's how archaeologists and people who are studying how old things that they've dug up can be, that's how they calculate, or it's one of the methods they use to calculate how old artifacts are. Now at the top of page 2 there are some quite difficult looking equations. What it amounts to in the end is if you have something that takes, for example, 10 years to double, then what your function should look like is you have the initial amount and you multiply by 2 to the power of however many years you're going on for, divided by 10. So if it doubles in 10 years, you would do t to the divided by 10 up here. And likewise, if it halves every 10 years, you would do you'd be multiplying by 2 to the power of negative t divided by 10. So it's always divided by however long it takes for it to double. So there's an example of that just here. Example 3 says that the population of houseflies doubles every 5 days. Now what that means is that you're going to have this kind of equation. You're going to have the population of flies is going to be equal to the initial amount of flies, 100, times 2 to the power of, now because it doubles every 5 days, that's why we've got the t divided by 5 up here. If you think about it, it kind of makes sense, because if it doubles every 5 days, that means that after 5 days it should have been multiplied by 2. So 5 divided by 5 would be 1, 2 to the power of 1 would be 2, so we'd be multiplying by 2. In any case, July has 31 days, so what you would do there was you would replace the t in that equation with 31. So you'd have 100 times 2 to the power of 31 over 5, and that would give you the population of flies. They multiply rapidly in summer, so you'd have over 7,000 flies by the 1st of August. That's assuming that it continues to double all the way through July. That might not be realistic, because in reality they might run out of food, but we're assuming that it's possible for them to do that. Now in this next example, example 4, we're talking about radioactive decay. We start off with 1,000 undecayed atoms, and we want to know how many will still be undecayed after 20 days. If the half-life of the substance is 8 days. That phrase means that every 8 days the number of undecayed atoms is going to halve. So we're told that there are 1,000 undecayed atoms to start with. That means that we're going to have n naught equal to 1,000. And then you can put that back into the equation. That means that if you're trying to find out the number after 8 days, we're going to have, or if it tells you that the half-life of the substance is 8 days, what you can write then is that n of 8, that's 1,000 times e to the power of negative 8k, is going to be equal to 500. And that equation then allows us to figure out what k is going to be equal to, here. So if we do that, we're going to have e to the power of negative 8k equal to a half. That's reasonably easy to solve. We can write that as e to the power of 8k equal to 2. There are other ways of solving this. In any case, you're going to rewrite that as 8k equal to ln of 2. But anyway, any of about 4 or 5 different ways you have of solving this should give you the same answer in the end. It should be roughly whatever 1/8 of ln of 2 is equal to. And once you've got that value, you take it, plug it back into your equation, right? And you are going to have something that looks like this, right? So we're now trying to figure out how many will remain after 20 days. So we've plugged in 20 in place of the t. We've now also got our k in there, and if we just evaluate this, what we should get is roughly 177 atoms are left. Now we could have done this equation, we could have set up the equation in a different way, but we were told at the start to start off with e to the power of. This question might have been much easier if it had been written as 2 to the power of something up here. It could have been written as n naught times 2 to the power of negative t over 8. And then it would have been an easier equation, easier problem to solve. However, we're given this, and given these facts, we're able to figure out what k is, and then we also know what n naught is, and we can use that. Now the last topic in this video is called Newton's law of cooling. And basically it just states that if you've got, say, a hot cup of coffee, and let's say that the initial temperature is quite hot, what's going to happen to that cup of coffee is it's going to cool down until it gets to room temperature. And we define something called the excess, which is the difference between the initial, whatever the initial temperature of the object is, or the temperature of the object, and the room temperature. So here's our example. Our example down here is we've got a cup of hot coffee at 80 degrees is placed in a room with a constant temperature of 20 degrees. So the room is at 20 degrees Celsius. The coffee initially is at 80 degrees. So you can probably guess what theta naught is. You can probably guess what this theta naught here is. It's the difference between the 80 degrees that we have initially for the hot coffee and the room temperature of 20. So this theta naught is going to be equal to 60. And our job then is to try and figure out what K is, and then use that later on. Okay, so let's try to set this up. So we've got this initial excess temperature of 60. So our law of cooling is going to look a little bit like this. Okay, so we have theta of t is equal to 60 times e to the power of negative kt. That's not so useful yet because we don't know what k is. However, we're told that after 7 minutes the temperature was equal to 60. So that tells us that the difference between the excess between the actual temperature and the room temperature is going to be 60 minus 20. So the excess, that thing that's denoted by theta, is going to be equal to 40. So in other words, this 60 e to the power of negative kt, when t is equal to 7, this whole thing here is going to be equal to 40. And that's the equation that we have here. We now have 60 e to the power of negative 7k is equal to 40. And from that equation, we are able to solve that for k and find out what k is equal to. Okay, so we have e to the power of negative 7k is equal to 40 divided by 60. We then simplify that a little bit. It could be written as e to the 7k equals 3 over 2. Again, there are 2 or 3 different ways you can find out what your k is equal to. You choose the one that suits you best. If this confuses you, you do it a different way. You'll get k equal to some value that should be approximately equal to the same as this, 1/7 ln of 3 over 2. Okay, once you've got that, you can plug it back in. Right? So your equation now is this thing where k is equal to 1/7 ln of 3 over 2. Now, the question is asking calculate the time taken for the temperature to go from 80 to 40. So it's now asking what's t equal to when the temperature is equal to 40. Now, when the temperature is equal to 40, the difference between 40 and 20 is 20. The excess is going to be 20. So what we do is when t is equal to 40, we have the excess equal to 20, and so we substitute that into the equation that we have above, into this equation here. And if we do that, what we're going to get is something that looks a little bit like this, which is an equation that we can solve, especially now that we know what k is equal to. So you take your steps, you try and simplify things. We've still got k in this, we haven't replaced k with anything, but at any point we can replace k with whatever value we found up here. Right, we keep on going until we get an equation that's t equal to something. Right, t is equal to ln of 3 over k. Finally, we've put in what we found for k here. We figure this whole thing out, this whole expression here, just on your calculator. You should get a value that's equal to 19 minutes.